Hello friends, today we are going to learn about chemical bonding and molecular structure. This is the audiobook. Important terms. Ionic bond, electrovalent bond. It is formed by transfer of one or more electrons from one atom to the other. The electrostatic attraction between the cation and anion thus formed constitute ionic bond. For example, in the formation of NaCl, one electron is transferred from sodium atom to chlorine atom. Lattice energy. It is defined as the energy released when 1 mole of crystalline compound is formed from its constituent ions. Lattice energy increases with increase in charge on cation and anion, with decrease in the size of ion. Covalent bond. It is formed by It is formed by sharing of one or more electron pair between same or different atoms. Covalent bonds can be single sharing of one pair, double sharing of two pairs, or triple sharing of three pairs. There is a tendency to complete the octet or duoctet by mutual sharing of electron. Covalency. The number of electrons of an element that is shared with the atoms of other element. Coordinate bond dative bond. Electrons of shared pair are contributed by one of the two bonded atoms called donor atom. After the bond is formed, it cannot be distinguished from a normal covalent bond. It is represented by an arrow pointing from the donor atom towards the acceptor atom. For example, NH3H plus gives ammonia NH4 plus. Octet rules. Every atom tends to acquire maximum stability by achieving noble gas configuration, octet or duplets through mutual sharing of electron or transferring of electron in the formation of chemical bond. Exception to octet rules. Many electron deficient compounds are stable where octet of center atom is not complete, such as BeCl2 beryllium dichloride BF3, which is boron trifluoride. Many compounds are stable where central atoms has more than 8 electrons in the valence shell, such as phosphor pentachloride, phosphor pentafluoride, sulfur hexafluoride, iodine subfluoride. Formal charge for an atom in the Levy structure. Formal charge is calculated as A, B plus half C, where A is the number of valence electron in free atom, B is the number of non-bonding electron, and C is the number of bonding electrons. Covalent character in an ionic bond. In an ionic bond, the cation and anion are not point charged. The electron cloud of the anion is loosely held as compared to that of the cation. Therefore, it is deviated towards the cation under the attractive influence of the cation. This is called polarizations. There is some sort of sharing of electron cloud now. This is the basis of origin of covalent character in an ionic bond. The cation is said to have polarizing power and anion is said to have polarizability. For Johnson, smaller the cation, greater the polarizing power. Larger the anion, greater the polarizability. Larger the charge on cation, greater is the polarization. Cation with 18 electrons in valence shell inert gas configuration cause greater polarizations than cation with the 8 electrons in the valence shell. Inert gas configurations for the same size and charge. Ionic and covalent bond. If there is a covalent bond formed between two atoms of different electronegativity, two shared pair of electrons is more attracted by one of them atoms. It acquires slight negative charge and other atoms acquire slight positive charge. The separation of positive and negative charge develop ionic character in the bond, and bond is now called polar covalent bond. Larger the electronegativity difference, larger is the ionic character. Percentage of ionic character is equal to 16 in bracket xa minus xb plus 3.5 in bracket xa minus xb square, where xa and xb are electronegativity of the atom A and B respectively. Xa is greater than xb. This is called Hannay and Smith equation. If the electronegativity difference is 1.7, the bond is said to be 50% ionic and 50% covalent. Dipole moment. The ionic character of covalent bond can be expressed in terms of dipole moment. Dipole moment is mu delta Q multiplied by D, where dq is the charge developed as a result of electronegativity difference and d is the distance between center of the atom. Dipole moment is a vector quantity. Unit of dipole moment is deba. Dipole moment and geometry of the molecule. Since dipole moment is a vector quantity, different bonds in symmetrical molecule may give rise to zero dipole moment because the resultant happens to be zero. Dipole moment and percentage of ionic character. Percentage of ionic character is observed dipole moment upon calculated dipole moment multiplied by 100, where calculated dipole moment is equal to E multiplied by D. Observed dipole moment experimental is equal to d by q multiplied by d, where d by q is fractional charge that developed due to electronegativity difference. Shape of molecule: triangular, planar, V-shaped, angular, bent, tetrahedral, bent, pyramidal, V-shaped or bent. Trigonal, bipyramidal, seesaw-shaped, T-shaped, linear, octahedral, square pyramidal, square planar, pentagonal, bipyramidal, distorted, octahedral. Valence shells electron pair repulsion theory, VSEPR theory. Electron pairs in the valence shell of an atom. Bond pairs or lone pair form. Charge cloud that repel each other such cloud of charge. Different type of electron pairs suffer different amount of repulsion. Lone pair. Lone pair repulsion greater than lone pair. Bond pair repulsion greater than bond pair repulsion. Under the influence of repulsion, the electron pair adjusts between in space when the repulsion is minimum. Molecule bond pair lone pair shape AB2 bond pair 2 lone pair 0 shape is linear. Molecule AB3 bond pair 3 lone pair 0 shape triangular planar. Molecule AB3 bond pair 2 lone pair 1 V shape bent angular. Molecule AB4 bond pair 4 lone pair 0 shape is tetrahedral. AB4 molecule bond pair 3 lone pair 1 shape pyramidal. Bond molecule AB4 bond pair 2 lone pair 2 shape V shape bent angular. Molecule AB5 bond pair 5 lone pair 0 shape trigonal bipyramidal. AB5 molecule bond pair 4 lone pair 1 seesaw shaped. AB5 molecule bond pair 3 lone pair 2 shape is T-shaped. AB5 molecule bond pair 2 lone pair 3 shape is linear. AB6 molecule bond pair 6 lone pair 0 shape is octahedral. Molecule AB6 bond pair 5 lone pair 1 shape is square pyramidal. Molecule AB6 bond pair 4 lone pair 2 square planar. Molecule AB7 bond pair 7 lone pair 0 pentagonal bipyramidal. Molecule AB7 bond pair 6 lone pair 1 distorted octahedral shape. Note, it is central atom and B is electron pair around it. Valence bond theory. Overlapping of atoms orbital of valence shell of atoms leads to the formation of covalent bond. Orbital containing one electron can participate in overlapping. Overlapping leads to increase in electron density in a region between two moles, which increase the attraction strength of the bond formed. Depend upon the extent of overlapping. Orbital with more directional nature, p orbital undergoes stronger overlapping than orbital with less directional nature, s orbital. And on overlapping leads to formation of delta of sigma bond, and sideway overlapping lead to formation of pi bond, sigma bond, pi bond. And on overlapping, pi bond sideway overlapping, sigma bond can be formed independently. Pi bond can be formed only after pi bond formation. Sigma bond stronger, pi bond weaker. Sigma bond greater overlap, pi bond is less overlap. Sigma bond is free rotation, pi bond is free rotation not possible. Hybridization. It is defined as a process of intermixing orbital of the same atom having similar or slightly different energy to give rise to a new set of same number of orbitals having equivalent shapes and energy, generally at time of chemical bonding. Regular shape and hybridization. Hybridization, shape, bond angle. Example: hybridization sp, shape is linear, bond angle is 180 degree. Example is beryllium dichloride. Hybridization sp2, shape is triangular planar, bond angle is 120 degree. Example is boron trifluoride. Hybridization sp3, shape is tetrahedral, bond angle is 109 degree 28". Examples: CH4, methane. Hybridization sp3d, trigonal bipyramidal, bond angle is 90 degree and 120 degree. Example is phosphor pentachloride. Hybridization sp3d2, shape is octahedral, bond angle is 90 degree. Example SF6. Hybridization sp3d3, shape is pentagonal bipyramidal, bond angle is 90 degree and 72". Example is iodine sept fluoride. dsp2 hybridization, shape is square planar, bond angle is 90 degree. Example is nickel tetracyano 2 minus ion complex. Distorted shape and hybridization. Molecule hybridization, bond pair, lone pair, shape of the molecule. SN difluoride, SnCl2, hybridization sp2, bond pair 2, lone pair 1, shape is V-shaped. Ammonia sp3 hybridization, bond pair is 3, lone pair 1, shape is pyramidal. Water hybridization sp3, bond pair 2, lone pair 2, V-shaped. SF4 hybridization sp3d, bond pair is 4, lone pair is 1, shape is seesaw shaped. ClF3, chlorine trifluoride, hybridization sp3d, bond pair 3, lone pair 2, shape is T-shaped. XeF2, xenon difluoride, hybridization sp3d, lone pair 2, lone pair is 2, shape is T-shaped. XeF2, xenon difluoride, sp3 hybridization, bond pair 2, lone pair is 3, shape is linear. XeO4, hybridization is sp3d2 hybridization, bond pair is 5, lone pair is 1, shape is square pyramidal. Molecule XeF4, hybridization sp3d2, bond pair is 4, lone pair is 2, shape is square planar. XeF6, hybridization sp3d2, bond pair is 6, lone pair is 1, shape of the molecule is distorted octahedral. Hybridization and shape of some ion. Ion hybridization shape lone pair. SO42 minus hybridization sp3 shape is tetrahedral, lone pair is 0. Ion CO32 minus carbonate hybridization is sp2 shape is triangular planar, lone pair is 0. Ion NO4 minus hybridization sp2 shape is triangular planar, lone pair is 0. Erythrin minus hybridization sp3d shape is linear, lone pair is 3. ICl2 plus hybridization sp3 shape is V-shape, lone pair is 2. Resonance. A single Lewis structure sometimes cannot represent the true electronic structure of a molecule. Resonance structures are then used to represent the true electronic structure. These Lewis structures are then called canonical contribution or resonating structure, and the real molecule is considered to be resonance hybrid. The molecule itself exists in single unchanging states embedded between the resonance structure. The molecule is only partially described by any one of canonical structure. Resonance hybrids are always more stable than the canonical structure. The delocalization of the electron lowers the orbital energy and provides stability. The gain is stability of resonance hybrid over the most stable of canonical structures called resonance energy. A canonical structure that is low in energy makes a relative greater contribution to the resonance hybrid. Molecular orbital theory, Hunts and Mullikins. In an atom, all orbitals are involved in bonding. Not only valence orbital, atomic orbital merge to give rise to a new set of molecular orbital MO. Molecular orbitals are formed by LCO in a combination of atomic orbital. Bonding molecular orbital antibonding molecular orbital formed by constructive interference or electron waves, formed by destructive interference of electron waves. Phi square equal to in brackets psi a square plus psi b square plus 2 psi a psi b. Antibody molecular orbital. Phi square is equal to psi a square plus psi b square. Antibody molecular orbital. Phi square equal to psi a square plus psi b square minus 2 psi a multiplied by psi b. Probability of finding the electron is more. Probability of finding the electron is less. Less energy in bonding molecular orbital, more energy in antibody molecular orbital. More stable in bonding molecular orbital, less stable in antibody molecular orbital. Favor bonding in molecular orbital, oppose bonding in molecular orbital. Bond order is equal to 1 by 2 half in bracket NB minus NA, where NB is number of electron in bonding molecular orbital, Na is number of electron in antibody molecular orbital. Higher the bond order, greater the stability. Higher the bond order, greater the bond energy. Higher the bond order, lesser the bond length. Molecular orbital diagram. Bond order half 10 minus 4 3 diamagnetic molecular orbital diagram for nitrogen molecules. Bond order half 10 minus 6 equal to 2 paramagnetic molecular orbital diagram for oxygen molecule. Total number of electron in dinitrogen is, as a nitrogen molecule, is 14. So in in the bonding molecular orbital, S1s is 2 electron, S1s is 2 electron, which is anti-bonding. Then in 2s2 orbitals, 2 electron are present in anti-bonding. uh, uh, 2s orbital, 2 electron are there. Then the highest orbital, which is px py, bonding molecular orbital, have 2 electron. Then in 2pz there is another 2 electron, but in an atom bonding molecular orbital, 2px 2py and sigma 2z, which is antibonding molecular orbitals, have no electrons. So total 40 electrons are there in dinitrogen molecule. In dioxygen, total number of electrons is 16. As we can see, in the bonding molecular orbital, 1s have 2 electrons. Their antibonding molecular orbital, 2 electrons are there. Then in 2s orbital, 2 electrons are there. Their antibody molecular orbital of 2s, 2 electrons are there. Then 5 2px, 5 2py, 2 electrons are here. Then in sigma 2pz, 2 electrons are there. Then antibody molecular orbital in 2px 2py, single cellular electrons are there. Okay, so in this way dinitrogen is diamagnetic because of absence of lone pair of electrons, and dioxygen is paramagnetic because of presence of lone pair of electrons. So both of this both of have different magnetism nature. Now in N2 plus, N2 minus, N2 minus, as per bonding electron, anti-bonding electron and bond order, we will going to learn about the magnetic nature. In N2, bonding electron is 8, anti-bonding electron is 2, bond order is 3, magnetic nature of nitrogen is diamagnetic. Then in N2 plus, bonding electron is 7, anti-bonding electron is 2, bond order is 2.5, magnetic nature of N2 plus is paramagnetic. N2 minus, bonding electron is 8, N2 minus, antibody electron is 3, bond order of N2 minus is 2.5, magnetic nature N2 minus is paramagnetic. N2 2 minus, N2 2 minus, bond electron is 8, antibody electron is 4, bond order is 2, magnetic nature is paramagnetic. Then the order of stability will be N2 dinitrogen in neutral nature is greater than N2 2 plus equal to N2 minus greater than N2 2 minus. Now here O2 oxygen, O2 plus, O2 minus superoxide, O2 2 minus peroxide, electron in bonding molecular orbital, electron antibody molecular orbital, bond order, magnetic nature. So we are going to learn about magnetic nature of different species of oxygen. So in dioxygen O2, electron in bonding molecular orbital is 8, electron in anti-bonding molecular orbital is 4, bond order of O2 is 2, magnetic nature is paramagnetic. Electron in bonding molecular orbital O2 plus is 8, electron in anti-bonding molecular orbital is 3, bond order of O2 plus is 2.5, magnetic nature of O2 plus is paramagnetic. O2 minus superoxide, electron in bonding molecular orbital is 8, electron in anti-bonding molecular orbital is 5, bond order is 1.5, magnetic nature is paramagnetic. O2 2 minus peroxide, electron in bonding molecular orbital is 8, electron in anti-bonding molecular orbital is 6, bond order of peroxide is 1. So the peroxide magnetic nature is paramagnetic. Order of stability is O2 plus greater than O2, greater than O2 minus, greater than O2 2 minus. That means O2 minus plus is greater than dioxygen greater than superoxide is greater than peroxide. Hydrogen bonding. Molecules involving a hydrogen atom bonded to a very small but highly electronegative atom such as fluorine, oxygen or nitrogen experience a special type of attractive special type attraction called hydrogen bonding. This bond is represented by a dotted line. Hydrogen bonds are much stronger than ordinary van der Waals interaction. These are much weaker than those of ionic or covalent bond. Association in water. Association in water. Oxygen atom of water molecule can form two hydrogen bonds. Each oxygen atom is joined to four neighboring H atom in a tetrahedral arrangement. Two H atoms are linked covalently. The other two hydrogen atoms are associated by hydrogen bonding. Structure of ice is rigid but open and present a cage-like framework. Molecules are not packed very close together and there are vacant spaces present in the structure. As ice melts, some of the hydrogen bonds are broken and the open cage-like structure collapses. The volume increase and density increase. Water therefore has a greater density than solid ice. Ice floats on liquid water with further increasing temperature. Density continue to increase due to breaking of more and more hydrogen bonds. Liquid water attains a maximum density at 4 degrees Celsius. Above 4 degrees Celsius, kinetic energy of the molecule increase and molecule move apart. This causes expansion. Therefore, the density of water starts decreasing again. Hydrogen type of hydrogen bonding. The formation of hydrogen bonding between two or more molecules of the same or different substance is known as intermolecular hydrogen bonding. For example, water molecule hydrogen bonding may occur between atoms within a single molecule. This is known as intermolecular hydrogen bonding. O chlorophenol, O nitrophenol, salicylic acid, chloral hydrate. O-nitrophenol is more volatile than para-nitrophenol because in ortho-nitrophenol there is intermolecular hydrogen bonding due to which it has lower boiling point, whereas pre-nitrophenol shows intermolecular hydrogen bonding.